Okay, so looking at question 3, this time on exothermic and endothermic reactions, it's asking us to look at a company is trying to find a reaction with a low activation energy to use in a hand warmer. So this is different to question 2 previously, which was looking at endothermic reactions. This is asking us to look at something which is going to be used as a hand warmer, and so we have to be thinking immediately that we must be having some sort of exothermic reaction, therefore something which has to give out heat. So getting into the question, it says define activation energy and describe how the activation energy is shown on a reaction profile. So if we answer the latter part of that first of all and use reaction B as the example, the activation energy is shown on these diagrams as the hill, essentially, between the reactants and the top of the peak. So for reaction B, it's quite a large activation energy. For reaction C, it's a little bit smaller, likewise for reaction A. But it is the hill you have to get over between the reactants and the maximum of the curve. Now this is then, in terms of defining that, this is a minimum energy. Okay, this is a minimum amount of energy that is needed. So minimum amount of energy in the first instance. And it's the minimum amount of energy which is required for a successful collision to occur. Successful collision to occur. Now, the key part to this is minimum amount of energy, because you can have more energy than is required. You just have to have the minimum amount of energy, which is again we've used in reaction B as the example. You have to have the minimum amount of energy required just to get you over this peak. If you've got more energy, then you've got more energy allowing you to get over, but ultimately you can still then come down the other side in terms of reaction and allow that to proceed. The actual activation energy, though, is the difference between the maximum on the peak and the difference in the reactants. Any more energy is literally just more energy than you required. The activation energy is the minimum energy, though, that you need for that reaction. So, allowing us then to go into question 3.2, which of these reactions is going to be most suitable for use in a hand warmer? Well, very simply, we can get rid of reaction C pretty quickly because the products are higher than the reactants. This is immediately leading us to think that this is an endothermic reaction, and therefore, in terms of a hand warmer, an endothermic reaction isn't going to be any good because it's going to get colder, so it's not going to warm your hands up. So reaction C is no good because it's an endothermic reaction. So that's not going to be helpful for us in this particular use, which means that we then have to look at A or B being good. And the two situations that we've got to look at is, one, the activation energy, and two, the difference in reactants and products, i.e. the amount of energy that's going to be released. The amount of energy which is going to be released in these two is the difference between the reactants and the products. And you can see that reactant A is going to give you more energy as released from the reaction rather than B, which is going to give you less energy. Also, reaction B has a higher activation energy. Reaction B has a higher activation energy, so it's going to be harder for that reaction to proceed in the first place. Reaction A is easier to proceed because it's got a lower activation energy, and it also gives you out more energy. So there's 2 points for A being better than B, really. A has a lower activation energy and also releases more energy. So it releases more energy than B. And that allows you to compare both of those together.